is, and we can essentially say, given what stimuli you could provide, like setting the chemical potentials of the composition for the temperature, which way the phase transformation is going to proceed. Okay, we need to provide thermodynamics all the different phases of the system as close to what is available in literature or as close to what is available in the experimental data. And there are different ways to do it. We have followed certain pragmatic ways of doing it, and that is what we are going to be learning about today in MicroSim. So this is something that all of you have studied now, that we are looking at this very course for thermodynamics, and all of you have known this particular thing, so I will not go into detail now. We are well past. What we are essentially interested in doing is how to integrate thermodynamic data in the software. Now, to understand this, you will have to first realize that including thermodynamics is something that you can choose to do in a very simplistic manner. So, for example, you can say, I don't really care about what is available in literature. Rather, I will create my own thermodynamics that is representing my temperature, representing my system, corresponding with some phase diagram calculations that are available. Okay, this is something that you can do. But typically, if you want to be realistic and pointed, people would really want you to have some link to existing thermodynamic data. Okay? Now, what are these databases? These databases are simple text files, right? What are referred to as typical .pdb files, right? Thermodynamic database files. And these thermodynamic database files, as you will see a little bit later, are essentially containing the information about how the free energy variation of the phases are with the composition. So they are essentially complete expressions of what the variation of these free energies are in given temperature intervals for people. This is what I thought we do. Now, there is a large group of data people working on this who sell these thermodynamic databases because it requires a lot of fitting to experiments, fitting to modeling experiments. And therefore, you can imagine that this can never be free because this is something that people will make money on. Therefore, you will find that most important thermodynamic databases are, although in principle available as text files, might not be available open to you, right? So it can only be available to you in encrypted form, right? What does it mean? It essentially means that you can have APIs extracting information relevant to the thermodynamics of the system through the APIs, but you will not have the free energy information. It's all its entirety to plug into thermodynamic database or basically software that you have. And just basically code that you have. Yes. Therefore, you need to strategize if you want to have plugin of thermodynamic information to work with both open databases, which have all the thermodynamic information now. So I'm going to be referring to that as unencrypted databases. Here. And also encrypted databases, where you don't have all of the information. But you can extract some of the information through APIs. Now, what are those APIs? These APIs are available through some of them, and some others will backstage. All of these essentially can work with DBs, and all of these companies, both of these, Thermocalc and Panda, they make databases. That's how they are there today. And through that effort, they essentially survive. But then these databases that they give to you is an encrypted form. So we will use their APIs to extract information. So this is the approach we will be doing. How to extract this information? There are multiple ways of doing it. I will use some of the ways that you will do, but we will essentially have to take a pragmatic way of approaches. If you want to unencrypted databases, these are open. All the PNP expressions are realistically available. So we have a converter in MicroSim, which is based on Python, which can extract using simple Python all the required expressions that you need for statistics. Okay. This is not a challenge. This, if it is available, is something you can do. But this is something that we work out to do. Okay. Modern matrix to MicroSim is something which is commercial software. Commercial has its own TQ interface which we have brought here. Extracting whatever information happens teams on the fly. Alright. As you can imagine, none of these are free, so you have to spend dollars or euros to buy. Okay. So this is how an open PDB looks, which is listed over here. This is the aluminum zinc PDB, and as you see, this is all the phases that are listed, and essentially it gives you expressions in the or coefficients of what are referred to as the deadly case of polynomials as a function of it. So it will give you one temperature range to another temperature range. What are the expressions for the different coefficients in the deadly case? The deadly case of polynomial is something that you can refer in classical polynomial textbooks and look at what those polynomials are. Why those polynomials? They offer a good basis set to basically span typical properties of our system. So people have stuck to that. And essentially what we go on doing is to go about a fitting exercise by attributing those thermodynamic coefficients. You try to fit what is listed out as properties of a given. So this is what CalFAT people do. And once the community of CalFAT agrees that a particular description fits well, they create a database and then plug it into their system. So this is how it looks. You have different all the phases written down and all the linear information transferred to this. Now this is something that you can now directly put into code. This is a text file, right? This is something that you can typically this TDP file would be as large as you please, depending on number of phases that you in the system and all. Okay. So it is not an easy exercise to convert whatever TDP you get into a code that you can finally run. So here is where we use PyCalFAT to convert this particular information into a code over here without essentially coming into between this file and this creation. Because creation is automatic. Okay, using this PyCalFAT, there's something which refers to a report generator. The report generator essentially in PyCalFAT directly converts this text file into this. Not only that, you can then ask the code to do symbolic operations using Python, using SymPy, to compute certain things like the differentials, which you need as a function in the case of solver, also as a code. All right. And that is very helpful because now a user in principle doesn't have to worry about this information transfer, which is actually quite a little large piece of work. Just can worry about, okay, once the code is there, he can directly plug it into MicroSim software, simple exercise, and go about running this one. Okay. So this is what we do when we use a particular thermodynamic function in our history approach to be referred to as function F2. Okay, so we have a key in what is referred to as an input parameter. An instance of that we saw yesterday when Pushkar was displaying the simulation. He opened the text file, that is essentially our in file, which is the set of all the input parameters that are plugged into the software before running. Okay. And one of the keys there is essentially function F, which alludes to what is the thermodynamic description that you are going to adopt to plug in. Okay. So in that function F2 refers to the formulation that you are doing an exact option, which means you take in the information of the TDP in its exact form and plug it into service. Okay, this is what you do. So, and here there's something that is relevant. Most of the solvers, most of the functions, there is no guarantee of convexity. That means C of U in principle may not be a single value. You can have situations where you can have visibility gaps and so on. So we calculate, we do take care of this problem. We essentially have local inversion of C of U nearby the equilibrium propositions, and this is done using GSL libraries. So although you don't have a functional form of C of U, you have numerical forms of C of U using local inversion. And this is therefore handling all sorts of reality from. It doesn't really matter whether you have a complexified function, different interval or not. Okay, then going to pragmatic approaches. Here is where we adopt. Instead of, and this essentially will come to the same case where you do not have the entire thermodynamic expression with you. and therefore we do not even try to get the entire computing expression for ourselves to work with. And as I will show you, it is not in some sense necessary to have the entire computing expression. So what we choose is referred to what is known as a parabolic approximation. And this parabolic expression approximation is essentially something like this, where the free energy of the phases is a function of C, and C is bold here. This is implying that it is all the k minus 1 components that are there in the problem. All right. And if you were to write a generic expression for the parabolic expression, it is essentially going to be something like this: Aij alpha Cij, which means it computes, it has all the components of this. Matrix Bj is corresponding phase and Cn. So the functional descriptions in the solver corresponding to 1, 3, and 4 have this as the description, right? 3 and 4 are essentially some differences exist in the way the coefficients are fitted to the actual Harvard database, but in principle, the functional forms for all of these functional keys are exactly the same. So what does this do? How do you extract this? You basically compute this Cij from the Hessian of the energies. So these Hessians, so what you do, if the PDB is available to you in open, you read in the PDB. And once you have the functional forms of the PDB, you can actually compute this using simplified directly. You don't need to do any other thing in between. You compute this directly as a function of temperature and see directly from the functional forms of the PDB level. Okay, so the Aij is, once you have the Hessians, you have Aij directly for each of it. So this coefficient can be fixed. And then what we do is to fix, we have the equilibrium compositions computed from the base diagram, and for those equilibrium compositions, you can fix Bj and Cj, Bj and C, such that the equilibrium represents exactly the phase line equilibrium phase composition. So, say this value here, this is something that directly gets me the right Gibbs-Thompson coefficient, because what is the Gibbs-Thompson coefficient? Gibbs-Thompson coefficient is relating to something which you saw with respect to the interfacial. The interfacial temperature is a function of beta V in 1D, but as soon as you move into a 2D situation, you have the curvature playing above, which means anything that is curved will have a depression of the medium. That is gamma. Essentially, the gamma is there over there. This is what we refer to as the fixed coefficient. That coefficient for an alloy, work it out, is directly related to the second derivative of the free energy, which is the Hc. And thereby, yet it is something coefficient, correct? In the actual experiment, or matching the experiment, you need to get this particular energy. Along with the surface energy also is common. So this is something, if it's there in the database, and you can plug it in its correctness, you essentially have tracked everything that is required with respect to the phase transformation, because the phase transformation in its entirety is most of the time diffusion control, and the temperature of the composition of the interface is essentially coming out from the Gibbs-Thompson coefficient. We have a Gibbs-Thompson coefficient which sets the correct temperature composition of the interface. The rest of it is the mobility of the diffusive mobility of the components in the liquid of the surrounding matrix, and that will come out of the mobilities that we do. Okay, but getting the correction to the thermodynamics is precisely this part. You get the Hessians correct, and you get the phase boundaries correct. You are coupling to the phase diagram, and the thermodynamics is any principle at right. It is typically all that is required for most casting equations where the certification is true.
Sir, here F alpha is an approximation to G alpha, right?
Yes.
So why do we have I less than J, not I equal to J in A alpha, like sigma kk?
I think it is I less than.
No, it should be I not equal to J.
Yeah, I not equal to. Yeah.
Okay.
So I do it I less than equal to J so that you don't double compute A21 and A1.
Okay.
A1, 2 and 2, 1 are strictly symmetric in this case, so we do only one.
Okay.
So it's the upper triangular matrix. But it needs the A11 also, A22 also. Upper triangular including the rank. No, sorry, lower triangle including the rank. So A1, so if it's a ternary system.
No, for a 4-component system, when I is 2, you are just using 3 and 4.
Let's do 3 components, which is having A1, 2.
Huh.
Okay, so 3 components, you will have A00, A11, A01. These are the 3 components.
No, the question is when the number of components are larger, say you have 5 components and I is 3. You're iterating for J is 4, only 4. There is a
Because
3,
I don't
4.
want 3, 4. I don't want 4, 3 and 3, 4 both to come.
No, there is no 3, 2.
There's nothing, 2, 3 will be there.
Okay.
So as long as I have 2, 3, 3, 2, I don't, as I said, in the matrix, you can think of it as a lower triangular.
Okay.
And including the diagonal. Okay, so that's essentially that. So with this, we get the connection to the thermodynamics correctly. There is a paper written by our group in current computing science 2015. We'll get the complete working out of this thermodynamic approximation and the connection. All the details, if you're interested, you can read that calmly, carefully, work out all details. Okay, so we take care of temperature dependence as we looked over here by, so this is the equilibrium compositions. So what we do is to take essentially a line calculation in the pan API. We do a line calculation at a given composition of the alloy, and you basically track all these solid liquid compositions at a given temperature, and then fit that with any spline, and then recreate essentially all of these coefficients corresponding to that. Right? So you will have all the information. So that's essentially what we do for function F4, where we do not have the databases. We can't compute those derivatives by hand or by any software. We need information coming from the APIs. From the APIs, you can extract what I said was the line calculation. So for a given temperature, you can find out all sorts of two-phase APIs you can have. So for example, here, let's see, you can try to basically calculate